Hello and welcome to yet another lecture on the NPTEL course on advanced plasticity of solid continua. So, in the last few classes we have been introducing to you the elements of convex analysis, and in the process we have also been talking of, at least initiated talking about, how rate independent plasticity can be modeled using certain elementary aspects of convex analysis. So, we will continue doing this in this particular talk as well and see how it works out. First, let us understand one thing that I have not talked of, that is the dual of the dual, right. So, we start with the dissipation function, which is phi j, right. J, if you recall, would be something like the plastic strain rate. It may include other velocity like variables associated with hardening as well. Then we basically found also phi star, which is the dual to the dissipation functional phi j. What about phi star star? It turns out that phi star star becomes the same as phi. So, in this sense, the Legendre-Fenchel transform acts like something like it, an involution. I will explain. Okay. So, first note that in the context of rate independent plasticity, the dual phi star is an indicator function over the set C. Also recall that the set C contains all admissible stresses, right, including stresses on the boundary of C. The boundary of C is nothing but the yield surface, and also recall that C has been a convex set, okay, is always a convex set, and since it is an indicator function, that is I am talking of phi star being an indicator function over C, that means phi star for all stress like objects, call them by the thermodynamic force x, for all x in C, phi star turns out to be 0. Outside of C, phi star takes a value of infinity. All this we have seen, right. Now, by definition of the Legendre-Fenchel transform, suppose I want to take the Legendre-Fenchel transform of phi star itself, then what should I do? I should call it by phi star star, right. That should be a function of the strain rate like object. Every time you take a Legendre-Fenchel transform, you typically, you can think of, you do something like a derivation in the sense that we take a supremum, right. So, in standard calculus for smooth functions, taking a supremum is taking a derivative, right. So, each time you take a Legendre-Fenchel transform, you switch from the original variable or a certain set of variables to the conjugate, right. So, when you take the Legendre-Fenchel transform of phi, then phi was originally a function of the strain rate j or epsilon p dot whatever. Phi star became a function of the conjugate to epsilon p dot or j, which is x or sigma, or that is the stress. Then when you take a Legendre-Fenchel transform of phi star also, again then it should become a function of the conjugate to sigma or x, which is j, right. So, that way you should remember. So, phi star star of j, right. By definition of the Legendre-Fenchel transform, we have this, that is supremum over all x, that is the thermodynamic forces belonging to the admissible set C, x j appropriate inner product, it could be a dot product also, or a or a Frobenius inner product, minus phi star x. So, you need to take the supremum by searching over all possible x for which the supremum is achieved, right. But we already know that phi star x equal to 0 for all admissible x. So, therefore, this goes off, and what you have is basically just the supremum over x of x inner product j. But by definition, this is nothing but the support function over the set C as a function of j, correct. That is the support function. You should recall the definition of the support function from our previous lecture. But this support function by definition is also phi j, right. So, because we find our dissipation potential phi j based on the support function over this set of admissible stresses, right. Therefore, we come back to phi j to be the same as phi double star j, right. Therefore, we say that basically, you know, we come back to the same object. This is not generally true. For example, here phi j is a strictly convex function. If you start with a convex function, then it is always true, that is phi double star will be equal to phi. But suppose in the cases which we have not discussed at all, where phi could be a non-convex function, then phi double star is not equal to phi. Phi double star will be the convex envelope kind of a thing of the non-convex phi, but we do not go into that. For our problem of interest in rate independent plasticity, phi is always convex. So, therefore, phi double star is always equal to phi. That is all we need, right. Now, let us also come to the issue of maximum dissipation, because maximum dissipation principle is a direct consequence of the Fenchel-Young inequality or equality, right. So, now let C be the set of admissible stresses. So, we have phi star x equal to 0 for all x belonging to C. Now, note that also phi j is HCJ, that is the support function of over C, that is by definition supremum of x times j, right, over x. Then, you know, if I take the subdifferential of phi del phi j, right, that is nothing but that will give me a stress like object, right, something like x or sigma 0 in this particular case, because plasticity is purely deviatoric in nature, incompressible plasticity. So, therefore, we only talk about the sigma 0, that is the deviatoric part of the stress, right. So, x is basically identifiable with sigma 0. So, when I talk of x, it is the same as sigma 0, the deviatoric part of stress. So, del phi j, this is something like the derivative gradient of phi j, right. That is nothing but arg max over all C of all sigma 0 of sigma 0 times j, inner product j. That means the result is a stress, right, because we are looking for that particular stress which maximizes sigma 0 inner product j and pick that particular stress out, and that is nothing but del phi j, correct. Or equivalently, we can say x belonging to del phi j essentially means that x must be within the admissible set, and this is very important, that x inner product j must be equal to phi j. Actually, this is nothing but a Fenchel-Young equality. There is also a phi star here, right, phi star x, but this is 0. This is actually equal to 0 over the admissible set C. We have already seen that, right, phi star is 0. So, therefore, that is gone. So, what we have is that the plastic work, which is x times j, x inner product j, is actually equal to the dissipation potential, and you really can't have any situation in which x times j can be greater than phi j, right. So, this is the maximum value that the plastic work can take. This means that the dissipation, you know, when actually x belongs to del phi j, that means when x is found by, let us say, when things are smooth, phi is smooth, then when x is found or the stress is found by taking the gradient of phi, then that particular stress must maximize the plastic dissipation such that the plastic dissipation so generated is equal exactly to the dissipation potential phi j. This is exactly the maximum dissipation principle, right, which comes out very neatly from the Fenchel-Young inequality. Recall that Fenchel-Young inequality tells us that x inner product j has to be less than equal to phi j, because phi star is 0. So, has to be less than equal to, so the maximum value is equal to phi j, correct. Right. So, please recall that, so the maximum dissipation principle is a requirement of the mathematics, basic mathematics of convex analysis. So, now we can actually prove this also, if you, this particular assertion, right, that is, it is true both ways. So, let us first assume that x, that is the stress, is a subdifferential of phi, all right. Then I need to show that x inner product j must be equal to phi j, correct. So, let us show that. So, assume that x belongs to the x is basically in the subdifferential of phi. So, this implies by definition of the subdifferential that there will be some h, because I am taking the subdifferential about the j, about at the point j in this strain rate space, right, in the plastic strain rate space. So, then by definition of the subdifferential, if I take h to be another strain rate, a quantity like j but not equal to j, away from j, then phi h must be greater than equal to phi j plus the inner product of x with h minus j, correct. So, that is the definition of the subdifferential, right. You please recall that. These if you want to follow these lectures, then learning by heart the things that have already been covered is a must, otherwise you will lose track. So, now this is just the definition of the subdifferential, right, x being the subdifferential. Now, I can take any value of h which is not equal to j, I can even take h equal to 0 or anything. So, first take h equal to 2j, right. Now, then because of the the local linearity of phi, because it is degree 1 homogeneous, no. So, by definition of degree 1 homogeneity, phi 2j must be equal to 2 times phi j, because the factor 2 comes out, and that must be because h equal to 2j. So, that must be greater than equal to phi j plus this. So, here recall that h has been replaced by 2j. Now, 2j minus j is just j. So, this means that phi j must be greater than equal to x inner product j, right. This is one consequence, assuming that x belongs to del phi j. Now, let us see something else. Let us choose h equal to 0. Then what do you have, because we already know that phi 0 equal to 0. So, phi h equal to 0, if h equal to 0. Then again use the defining identity for the subdifferential, that is phi h greater than equal to this thing, phi h greater than equal to phi j plus x times h minus j, x inner product h minus j, where h in this particular case is 0. Then this is 0, phi h is 0, phi j you have here, there is h is 0 again here, and then you have minus x inner product j. So, if you put them together you get phi j less than equal to x inner product j. So, we have two contradicting assertions. Once we get phi j greater than equal to x inner product j, then we get phi j less than equal to x inner product j. Both can be simultaneously true if and only if they are equal, right. So, therefore, phi j is equal to x inner product j. So, the assertion is proved in the forward direction. Now, I need to show the assertion to be valid in the opposite converse direction. So, for that let us assume the opposite, that is from the, starting from the opposite side, that is, let us assume that x inner product j is phi j. We need to show that if that is true, then x belongs to del phi j, right. So, for any arbitrary h, therefore, because if x has to belong to del phi j, then it has to satisfy the definition of the subdifferential, right. So, let us put the definition. So, for any arbitrary h, we must have this inequality as usual, the usual definition of the subdifferential. Now, since x is in the admissible set of stresses, therefore, phi h, correct, because x is in the admissible stresses. So, phi h by definition, because what is the phi h? It is the support function over the set C. So, by definition of the support function, it is the supremum over all sigma, basically sigma 0, that is the deviatoric stress, sigma inner product H, right. But this is the maximum value that this product can take, because this is the supremum. So, for any choice of x, I can safely say that this quantity has to be greater than x inner product H, correct. So, therefore, we can say that phi H is greater than equal to, because phi H was this side, right. So, phi H is greater than equal to x inner product H. Now, x inner product H is actually equal to x inner product, because you can just write it in this trivial manner, that is x inner product j plus x inner product H minus j. You see, x inner product j cancels from both sides, from this, you know, x inner product j appears here, there is an x inner product j here, correct, they cancel. So, all you have got is x inner product H, that is all, you know, I have written it in another way, right. Now, we already have started with the assumption that x inner product j is equal to phi j. So, instead of this x inner product j here, put phi j, okay. So, then we have phi h is equal to, greater than equal to phi j plus x times, or inner product with H minus j. But this is exactly the definition of the subdifferential. When x belongs to the subdifferential of phi at j, then this inequality is valid from the definition of the subdifferential. Therefore, x must belong to the set of subdifferentials of phi, right. So, that is what we wanted to prove. So, both are proved, the forward you know, argument as well as the converse. So, you see, so basically what we are talking of, you know, so far is that whenever you get the stress like object, or in general thermodynamic force from the subdifferential of phi, then you get the maximum possible dissipation. You cannot have that much of dissipation for any other thing. So, since the thermodynamic force is always found in continuum plasticity by taking the subdifferential of the dissipation potential, therefore, it shows that the actual plasticity flow is such as to maximize the plastic work, the plastic dissipation. That is a very interesting thing, right. So, it follows directly from the convex analytic tools. Now, let us come to the issue of Tresca plasticity, because Tresca plasticity is a case in which the yield surface is non-smooth. And let us start with the dissipation potential. How do you find the dissipation potential for Tresca plasticity? Let us, so all that you have to find is basically the support function Hc. Recall that the Tresca yield criterion consists of several segments: max over ij's, modulus of sigma I minus sigma j less than equal to 2k, where k is the yield shear stress. Okay. Now, for different choices of I and j, you remember that what is I and what is j. I mean, basically what is sigma I and what is sigma j. I will just, you know, recall to your mind that sigma I etc. are the principal values, principal stresses corresponding to the stress tensor, all right. In fact, corresponding to the deviatoric stress tensor, all right. These are the principal values. So, you know, the C, therefore, the set of all admissible stresses is clearly the set of all this sigma 0, such that for all ij's this has to be valid, right. So, you see each for, so choose one I and choose one j. Let us say I equal to 1, j equal to 2. So, for that particular case you will be having a modulus of sigma 1 minus sigma 2 less than equal to 2k, right, something like that. That will give one, you know, one kind of a surface. Then choose another I and j, that will give another surface. When such surfaces meet with each other, they must meet at a ridge, right, one surface meeting another at a ridge, at a kind of in 2D it is like a corner, right. So one expects therefore automatically such a hexagonal structure coming up in 2D or a or a polyhedral structure coming up in 3D or in higher dimension. Alright, so this is the reason why Tresca plasticity, based on the very definition of the yield criterion, we get this polyhedral nature of the set C. Now recall that from definition of phi j, that has to be equal to hcj, which is the support function over C, and j is nothing but epsilon p dot, the plastic strain rate, and let now j1, j2, j3 be the principal values of the plastic strain rate j, okay. Just as sigma 1, sigma 2, sigma 3 are the principal values of sigma 0, the deviatoric stress. Similarly, J1, J2, J3 are the principal values of the plastic strain rate. Since the flow is incompressible, therefore we can safely say that J1 plus J2 plus J3 is equal to 0, right. Therefore I can simply say that phi j is supremum over all such principal values sigma I, sum over I equal to 1 to 3 sigma I j I, right. So this is the same as this is how I can construct sigma j instead of doing a more complicated supremum of sigma 0 in a product j. In terms of the eigenvalues I can do that. Right. So now let us have the yield criterion expanded properly. So let us take I equal to 1, j equal to 2, so we have one yield condition. Then similarly another yield condition, similarly a third, sigma 3 minus sigma 1 less than equal to 2k. Now by taking the negatives I will be getting 3 more. So there are 6 such component conditions, right. So the supremum, so basically these component conditions are like surfaces that meet at ridges and create a polyhedral set. So the supremum of phi j actually will be such that the stresses, these actually principal stresses must belong to the corners or the ridges, right. So this is a very important thing. So in this particular case there is no collinearity of the strain rate j or epsilon p dot with sigma 0, right, they are not collinear, right. So first let us then find these 6 vertices. These 6 vertices are minus k or k minus k 0, then I may go on doing this k 0 minus k, 0 k minus k, then minus k k 0, minus k 0 k and 0 minus k k. 6 vertices are there, right. So since I know that phi j, that supremum in the definition of phi j is achieved at those corners or these ridges or these at these 6 vertices, so we can actually evaluate the inner product, because that is what actually is happening. So that supremum reduces to finding the maximum over these possibilities, right, naturally. So k comes out because k is constant, and max of j1 minus j2, j2 minus j3 and so on, right. You see this is a pretty neat derivation from the original requirement of the definition of phi j. This is a simpler form. We can further simplify it, but to do that let us first order j like this. J1, let us put it at the top, that means the highest value of the principal value is j1 in terms of the magnitude. So j1 must be positive because their sum has to be equal to 0, right. Then j2 and j3, remember that j3 has to be negative because the sum is 0, no. So j2 can be positive or negative, right. Now you can also see therefore there are just 3 values, right. This is a real line, this is my j1, this is j2 and this is j3, which is definitely less than 0 and this is greater than 0, right. So the max of ji minus jj must be equal to j1 minus j3, that is it, you can clearly see that. Therefore I can simply say that phi j is k times j1 minus j3, so far no problem, further simplified. Now, there is another thing. It also turns out that if you take this modulus of these 3, modulus of J1 plus modulus of J2 plus modulus of J3, that is actually equal to 2 times J1 minus J3. One way of seeing that is just take J2 equal to 0, then J1 equal to minus J3 or J3 equal to minus J1, and then this is obviously true. 2 times J1 minus J3 must be equal to the sum of the moduli of this, right. So, this is always true, because otherwise if it is J2 is not equal to 0, then we can always translate it, translate the whole thing appropriately. So, this is always true. Okay. Now, therefore, I can, instead of k times J1 minus J3, I can simply say phi j, there is a half that will come, but k is a material constant. So, let us incorporate that half within k and call it k. So, therefore, phi j I can call as k times modulus of J1 plus modulus of J2 plus modulus of J3, right. Now, comes the final part, that we have already seen that the sum of the absolute values, right, J1, J2, J3 is actually equal to, so is actually equal to twice the largest value of this J1 or J3. You can see it from these facts. Let us say J2 equal to 0, then J1 has to be equal to minus J3. So, therefore, this distance is equal to, in that case, this distance, right. So, therefore, twice of this is equal to sum of J1, J2, J3, correct, the absolute values. So, this is exactly what we have. So, therefore, phi j finally can be written in this very simple form, which is 2k, 2 is a factor because twice the largest value of J1 etc. has to be taken, right. 2k times max of modulus of J1 comma modulus of J2 comma modulus of J3. This is the final form of the Tresca dissipation potential. It is a pretty still a complicated form, but much simpler than what we started off with, correct. So, what actually is happening with the Tresca plasticity? Let us take a look from the convex analytic perspective. So, think of the situation on the 2D plane. So, this is a deviatoric stress axis 2, this is the deviatoric stress axis 1, and the Tresca plasticity, typically the yield surface in this particular case becomes a hexagon, perfect hexagon. This is my yield set C, right. So, if it turns out that the stress is, suppose I take the stress, so suppose the yield stress is somewhere here, right. So, at this corner, how will the strain rate be directed? In usual circumstances, remember, this is my yield set, yield surface. So, the strain rate must be perpendicular, right, to the tangent at this point. But here there is no tangent at this corner, no. So, because it is not possible, because there is a non-smoothness here. So, what do? You find the normal cone here. I have already defined that in my one of the last lectures. What it is, the normal cone is, in this particular case, the normal cone to the indicator function over C at this particular point, at this particular sigma, right. So, call this as sigma. At this point, find the subdifferential, and that turns out to be this particular set. Draw a line which is normal to this axis first. So, that is N1. Draw another normal to this axis, that is N2, on this face, I am sorry, this face, that is N2, and on this face it is N1, right. In between, including N1 and N2, all are possible valid directions for the plastic strain rate. It can be anywhere, you do not know. You do an experiment, once you will be finding it in some direction, you do another experiment, you will be finding it another direction, right. So, this is a non-uniqueness of the plastic flow direction because of the non-smoothness of the yield surface, which we did not find in von Mises plasticity. Okay. So, this is an important point. So, now we come to another issue, which is to find the plastic strain given the strain increment, but that is another issue altogether. So, we will do that, but till we actually go into that, we will try to assimilate whatever we have studied so far and take a breather here and come back for the next lecture. So far we have actually been discussing only about the Tresca plasticity, I mean mostly other than the maximum dissipation principle. But now we will move on from the Tresca plasticity and assume that again we have this von Mises flow rule, and then given the total strain increment, I want to find how I want to find the plastic strain rate, strain increment. That is what we will be doing in the context of von Mises plasticity in the next lecture. Till then, thank you very much for listening in.